This is AQA AS Physics 2020 paper 1. As per usual, can't show the paper on screen because otherwise AQA will get the whole channel deleted like they almost did in the past, but link to the paper and mark scheme are in the description. 1.1. We have a strong interaction here. So we want the lepton number, strangeness and charge of X. Well, nice easy one to begin with. Strangeness, none of these have strange quarks in. And so therefore, X must have a strangeness of 0 as well. Lepton number, this is a strong interaction, so by definition, we can't have any leptons involved. So charge is the only one that we have to think about. We have plus 1 goes to plus 1, minus 1. So therefore, if we have here 2, we have 2 here as well, then that means that it must have a charge of plus 1. 1.2, identify the particle. Well, it's got no strangeness and no lepton number. It could be a meson. However, we're going to have to invoke baryon number as well, because that was spuriously missing from our thingy above here. So baryon, we have 1 plus 1 goes to 1. Pion is a meson, so therefore that means that we must have a proton coming out as X. It is a proton. 1.3, possible decay of a negative pion is this. What is particle Y? Well, we know that whenever we have an electron being made, we pretty much always have some sort of neutrino being made. So lepton number is 0. That goes to plus 1 because the electron is the OG lepton, as it were. So therefore, this must have a lepton number of minus 1. Must have a charge of 0, of course, because this is minus 1 goes to minus 1 plus 0. So yes, it's going to be an electron neutrino, but it's going to be an anti-electron neutrino. So therefore, it's the top box. 1.4. Oh no, a 6 marker. What are we being asked to talk about? Hadrons. So we need the properties, structure, and stability. Okay, hadrons first of all. We have mesons and we have baryons. Mesons consist of quark-antiquark pair, whereas baryons consist of 3 quarks. I guess we've skipped straight to structure there, haven't we? Let's talk about properties. Well, they interact through the strong nuclear force, not the weak force, because that's 4 leptons. We said they consist of quarks already, so we don't need to say that again. And then I guess all we have to talk about is stability. So really, the only stable baryon is proton. And we can say mesons and other baryons decay into other hadrons, e.g. the one that we saw above. Bit of a rubbish 6 marker, I've got to be honest. There's not a lot we can write there. I guess we've got 6 little points there, that'll do. 2.1, spacecraft entering atmosphere. We have a mass of 610 kilograms. We have a speed of 5.5 kilometers per second. Do you know what? I'm going to write just 5,500 meters per second. Calculate the kinetic energy. Okay, easy. This is a year 9 question. Half mv squared. So that is half times 610 times 5,500 squared. Wow, that's a lot of energy. What's that? 9 point... Let's go to 2 sig figs because our data has been given to a minimum of 2 sig figs. So 9.2 times 10 to the 9 joules. Wow, it is booking it. 2.2, parachute opens. Staff parachute, blah, 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 blah. Explain with reference to Newton's laws of motion why displacing gas causes a force on the system, why this force causes the system to decelerate. Okay, this is all to do with momentum, isn't it? It might not mention momentum, but it is. So we can say that collision of parachute with the gas particles causes them to gain momentum. Therefore, as force is equal to rate of change of momentum, parachute exerts force on particles. Due to Newton's third law of motion, that is, equal and opposite forces, always true, particles also exert force on parachute in opposite direction. But we're not done yet because we need to talk about How does this actually slow down the parachute and the spacecraft? Newton's second law, we've already kind of talked about it already up here. This is Newton's second law really. Is the second law really? Just rejigged. Therefore, resultant force on parachute causes it and spacecraft to decelerate. There we go. There's a couple of different ways you could have worded that as well. Maybe we could have talked about acceleration of the particles, etc. But we've got 4 points there. 2.3, falls through a vertical. Oh, this looks like, is this actually SUVAT? I don't know. So we have a height of 49 meters and a difference in energy of 2.2 times 10 to the 5 joules. During this time, wait, what? 3.3 times 10 to the 5 joules transferred to atmosphere. Oh, sorry, it loses 2.2 times 10 to the 5 joules of kinetic energy. Right. Okay, we have the mass as well. This is not a super easy question. There's lots of things going on here. And so we're being asked to find out G. So we know that total energy lost by the spaceship is going to be equal to the total energy gained by atmosphere. We have the total energy gained by the atmosphere, 3.3 times 10 to the 5. But it's not only GP that's being lost, it's kinetic energy that's being lost as well. So we can say GP lost plus KE lost equals energy gained by atmosphere. We know that GP is equal to mgh, and the KE lost was 2.2 times 10 to the 5. And then that's equal to that 3.3 times 10 to the 5. So, taking this over the other side, we're going to end up with 1.1 times 10 to the 5. All we then have to do is take m and h over to the other side, so therefore, acceleration due to gravity is going to be equal to 1.1 times 10 to the 5 divided by our mass times that change in height. And that gives us to 2 sig figs, 3.7 meters per second squared. Not a super easy question. Involves a little bit of thought as to what's going on, but whenever it comes to energy questions, just start off with this. Just write out what energy is going in, what energy is coming out, and then it'll all start to make sense. 2.4, dust from the surface can enter the atmosphere, increases the density. How does an increase in dust affect the deceleration of the system? So dust equals heavier particles in atmosphere, therefore require greater force to accelerate them by parachute, therefore greater force exerted on parachute in opposite direction, therefore faster deceleration. 3.1, we have a golf ball going into a hole. Golfer hits the ball, so it moves with initial velocity of 1.8 meters per second. Ball experiences a deceleration of 1.2 meters per second squared. Calculate the velocity of the ball when it reaches the edge of the hole. Okay, so we also have the distance as well, 1.3 meters. We're being asked to find the final velocity, so we're looking for v. So yes, this is SUVAT, we don't care about time, so we're going to be using v squared equals u squared plus 2as. Therefore, v is going to be equal to the square root of all that. So that means that v is going to be equal to the square root of 1.8 squared plus 2 times, now I have made a bit of a mistake. The initial velocity is obviously to the right, and so that means that we have a positive velocity to begin with. I've written the acceleration as 1.2. Of course it's not, is it? It's minus 1.2. It's slowing down. So it's going to be times by minus 1.2 times 1.3. So that gives us 0.346 meters per second. Let's round that to 0.35 meters per second. 3.2, we're trying to get out of this bunker. The horizontal component of u is 8.8 meters per second. Okay, so let's draw it out again here. We have the actual velocity. We have the horizontal component. We know that's 8.8 meters per second. And we're looking for the vertical velocity. And this is 35 degrees. So this is one of the few times where it's probably not worth using my easy vectors trick. Let's just move this vector over to here. We're looking for this. So therefore, this is the opposite. So the adjacent, this is the hypotenuse. We don't care about the hypotenuse, so of course we're going to be using tan. So we're going to say the tan of 35 is equal to the opposite over 8.8, which is the adjacent. Therefore, I tell you what, shall I call this V? There we go. Therefore, V is equal to 8.8 tan 35. And sure enough, that gives us 6.2, let's say, meters per second. 3.3, we're back here again, and now the ball is going up here. Calculate the time for the ball to travel to X. Of course, we're not concerned with what's going on horizontally. If it's traveling horizontally at that point, then it has no vertical velocity, so therefore it's reached its apex, so therefore we know that we're just going to be dealing with vertical SUVAT here, so we have SUVAT. We know that V is going to be 0. We just calculated U as 6.2 meters per second going upwards. We know acceleration is minus 9.8 meters per second squared because of course gravity is trying to pull it back down, it's getting slower. We're looking for time, so therefore we're going to use V equals U plus AT. Rearranging that, we have T is equal to V minus U over A. So that's 0 minus 6.2 over minus 9.8. So the minuses cancel, and we end up with 0.63 seconds. 3.4, we're looking for the distance now, so therefore we can use what we want. Let's use average speed times time. So that's just 6.2 over 2 times the time of 0.63, and that gives us a distance of 1.95 meters. I want to round that up to 2, but the mark scheme says 1.9 because they of course used 6 in their calculation. They usually use their rounded value, but you'll get the mark either way. 3.5, we now want a trajectory, which means that it has a lower horizontal velocity at the top. So we're going to have this trajectory here. And why is that? It's because the initial angle to the horizontal is greater. Therefore, horizontal component of the velocity is less. And then that will also stay the case all through the flight and at the top as well. 4.1, we have two isotopes of boron. We have a charge and we have a specific charge. We know specific charge is the same thing as charge to mass ratio. And so we know that's equal to Q over M. We're looking for the mass. So therefore, just swapping those two round, the mass is equal to charge over specific charge. And so that's going to be just the 1.6 times 10 to the minus 19 divided by 8.7 times 10 to the 6. And that gives us 1.8 times 10 to the minus 26 kilograms. 4.2, determine the number of nucleons in the nucleus. We can see that the mass of one nucleon is 1.7 times 10 to the minus 27 kilograms. One of those times when units are your friends, let's make up a unit. So we're going to say kilograms per nucleon. We have kilograms per nucleon. We have kilograms. We want nucleons. Therefore, we're going to do 1.8 times 10 to the minus 26 divided by 1.7 times 10 to the minus 27. This is kilograms. This is kilograms per nucleon. Kilograms cancel. Nucleons end up being on top. The sort out in powers of 10 minus 27 on the bottom, so add it to the top. So it's just going to be times 10 to the 1 on top. So that is the same as 18 divided by 1.7. And that gives us, oh, that's not nice. They should have done a better job with this. 10.6. And so we're going to say that that's going to be 11. It's really mean though, giving us numbers that are that close. 4.3, compare the composition of X and Y. Well, of course, they have the same number of protons because they're the same element. But of course, X has more neutrons because it is heavier. 4.4, ions of Y have the same charge. How does the specific charge of an ion X compare with that of an ion of Y? Well, we said that specific charge is equal to Q divided by M, charge to mass ratio. We know that for X, M is heavier. Therefore, if we're dividing by a bigger number, X has smaller specific charge. We could say that specific charge is inversely proportional to mass. So therefore, heavier mass, smaller specific charge. 4.5, we have samples. Which sample contains a greater percentage of isotope Y? Well, they all have the same charge, so we're not fussed about that. So we want to know what the mass is per ion in both of these. So let's do 1. Let's do kilograms divided by number of ions. And that gives us bang on 1.8 times 10 to the minus 26 kilograms per ion. And then for 2, that gives us 1 point. Ooh, okay. They're close, 1.77 times 10 to the minus 26 kilograms per ion. Therefore, ions in sample 2 are lighter on average. Therefore, it has greater proportion of isotope Y in it. Question 5, bit of electricity. We have an EMF of 1.5 volts. We have an internal resistance of 0.65 ohms. We have, we just want to know what the EMF is. What's the definition of EMF? Well, we know that just like any voltage is energy divided by charge, so it is therefore energy supplied to every coulomb of charge that passes through the cell. Easy. 5.2. Current in the circuit is 0.31 amps. We want to find the total power output of the cell. Well, power is just equal to, well, this might seem easy, but you might get caught out. Power, we can say, is of course VI. And so if we're talking about V in this case, we're talking about the EMF, that's the total power output. We can't use I squared R because, well, we'd have to use the internal resistance, but that's just going to be the power lost in the battery. So that's not what we want. Sure enough, that gives us something close, 0.465 watts. 5.3, we're being asked to find the power dissipated in the load resistor. Now, they haven't said that. They've said energy dissipated per second, but they're just trying to catch you out. They really are just asking for power. It's just AQA being jerks, as per usual. So there's a couple of different ways you could do this. We could crack out the equation, find out the resistance of resistor R, but seeing that we have a power here, let's find out the power lost in the cell. That's going to be I squared little r. So it's going to be 0.31 squared times 0.65, and that gives us 0.062 watts. So therefore, we know that the power available for resistor R is going to be that total that the battery is producing, take away the power that's lost due to the internal resistance in the cell. That gives us 0.403 watts. They haven't really been too fussed with sig figs in the mark scheme, so we're not going to be either. If we wanted to be though, we do it to 2 sig figs. 5.4, we're being asked what is the maximum time for which the battery can run for. Everything else is staying the same. We know that the energy is 14 kilojoules. So I'm going to say that's 1.4 times 10 to the 4 joules. And what else do we know? Well, we know the power, but if E is the total energy, then we need P being the total power. And so that's going to be our 0.47 from question 5.2. And we know that power is a rate of energy transfer, so it's just going to be that. We're looking for time, so swap these over. So therefore time is equal to energy divided by power. So it's 1.4 times 10 to the 4 divided by 0.47. And that gives us, well, the 2 sig figs anyway, 30,000. So 3 times 10 to the 4 seconds. 5.5, we have 2 batteries or 2 cells. We have a lamp there. Okay. What are we being asked? Yeah, 1.5, fine, 1.5. We also have the 0.65 ohms for both of those two. The lamp is rated at 1.3 volts and 0.8 watts. Deduce whether the circuit can provide the lamp with 0.8 watts of power at a potential of 1.3 volts. Okay, assume the resistance of the lamp is constant. Okay, the first thing we need to do then, we're going to forget about that for now because we're being asked to prove that it's 0.8 watts. So what we're going to do is crack out our equation. Epsilon equals, I'm going to say V this time, plus IR. So what do we know out of these then? Well, we know that the EMF is just 1.5 volts because they're in parallel. V is going to be 1.3, that's what we want for the lamp. Resistance, internal resistance, well, we have 2 of them in parallel. So you should know 2 identical resistors in parallel. It's going to be half altogether, so it's going to be 0.325 ohms. We're looking for I, so therefore, rearranging this, I is going to be equal to EMF minus the terminal PD divided by the internal resistance. So that ends up being 0.615 amps. So we know the current flowing through the circuit and therefore the lamp as well. Therefore, we can find our power in the lamp. So it's just going to be our 1.3 volts times 0.615 amps. And sure enough, that gives us bang on 0.8 watts. Happy days. 5.6 we're being asked what would happen if we added more cells. More cells would mean a smaller current flowing through each one. Therefore, power lost in each cell reduced. Also, more cells equals more energy stored or more energy available. Therefore, both these things together would mean that the lamp would stay on for a longer time. We can add in here our cells in parallel, EMF is unchanged. We can say also V will not exceed that of individual cells. 6.1, we have this setup here, have a string. We're looking for the second harmonic, so therefore the second harmonic is going to look like this. So therefore at this point, P's up here, Q's down here. So we know that P and Q oscillate pi radians out of phase, or we could say in antiphase, same thing, and with same amplitude. And they're going to be moving in opposite directions at any given time, aren't they? 6.2, we have a wave. We know that the frequency is 250 Hertz. What's the wavelength going to be? Well, how many waves do we have here? 1 and 2. So this is lambda, this is lambda. So therefore, 0.55 meters equals 2 lambda. Therefore, lambda is going to be equal to 0.275 meters. Using our wave equation, V equals F lambda, or C equals F lambda, so that's 250 times our wavelength. And we end up with a wave speed of 69 meters per second. 6.3, we're being asked, what must the waves be doing in order to undergo superpositioning in this way? Well, we know that the waves must have same wave speed, frequency, and therefore wavelength as well. Same amplitude if they are to actually make that perfect wave. They don't need same amplitude to make a stationary wave, but to make a perfect one like that, they must have that. And also the waves must be moving in opposite direction. 6.4, we have one wave that's like this, and the second wave is like this. So we're magically being able to see the two waves. What happens if they're added together? Well, we can see that peaks are lining up with troughs in the opposite wave, and so therefore they're going to add up to 0. So it's just a flat line. Crazy. 6.5, we're being asked, where are the antinodes? Not a very easy question, actually. Now we need to think what's actually happening. Let's say that this wave's going this way, this wave's going to the left though. In a fraction of a second's time, where are these points on the end of the string going to be? Well, if the wave's moving to the right at the top, then that means that this bit of the wave here is moving across, and so actually it's now going to be like this. So therefore, point P is actually going to be up here. What about at the bottom? Well, if this is going to the left, then that means that, well, the wave is now going to be here. So actually point P is going to be up here as well. So at the ends, both points are going to be at the top in a fraction of a second's time. So they're going to be up here. It's going to be the opposite for these points here. Actually, what you find is that where they line up peaks and troughs, we end up with a node. So that means that in all the other places, we must have antinodes. So we have 1, 2, 3, 4, 5. So all you need to do is put 5 crosses on there. That is not an easy question though. 6.6, we're being asked what happens when you change mu, mass per unit length of your string. Here's our fundamental mode or first harmonic equation. What we can see is that mu is going up by times 9. So that means that this whole thing here goes down by a factor of 9. So that means square rooting that whole thing goes down by a factor of 3. But we're told that the frequency is actually staying the same. So that's only partially useful. We want to know what harmonic we get. And you can probably see what it's going to be. We can see that we have the first harmonic here. So you can probably guess what it's going to be, can't you? However, let's try and be a little bit more scientific about it. This, of course, is wave speed. So V is equal to root T over mu. So that means that V is proportional to 1 over root mu. So similar to above, this is going up by a factor of 3, square root of 9. So that means that the wave speed must be going down by a factor of 3. And then using our wave equation, v equals f lambda, frequency staying the same. If the wave speed is going down, therefore so must the wavelength. So that means that the wavelength has gone down by a factor of 3 for the same frequency, so we should end up with smaller waves. This is, of course, the third harmonic. So there you go. Hope you found that helpful. If you did, please leave a like. Consider donating via the super thanks button to help me keep making these past paper videos to help you guys. Click on the card if you want to go to the playlist with all of the AS papers on. Join the Discord if you need some extra help. Link in description. Good luck with your revision, and I'll see you next time.